It's good to see everybody. I hope you guys are doing okay. I hope you had a great weekend. I wanted to button up a couple of things on our last, from our last class. And then I thought I would talk a little bit about transistors. And part of my goal for that is because this week I assigned a short video and a short but very, very, very dense article on semiconductor chip manufacturing. And so I wanted today to put some context. Your homework is due tomorrow. And then on Wednesday, I'm going to go over the homework and maybe do a couple of other things related to that and related to Friday. So we've been learning about working with components, passive components, resistors and capacitors. We're making use of complex notation right off the bat. We are last times we looked at a voltage source connected to a capacitor and a resistor. We know that the capacitor has an inductance that's inversely proportional to the frequency. So as frequency goes up, this denominator gets big and the impedance or the presence of that capacitor goes down. And so we looked at this as a voltage divider, a generalized voltage divider. We went through exactly the steps that we had with the two resistors there. And we developed a relationship for the output voltage divided by the input voltage, the output over the input as a function of frequency, and in terms of the resistor value and the capacitor value. And very interestingly, we saw this connection, this omega RC. And if we look at the units of this piece down here, we see that it's dimensionless because we're adding it to 1, which has no units. And so this relationship to omega and to RC is very, very magic. And so we talk about RC as being a unit of time because time times frequency is dimensionless. And so we have an RC time constant associated with this this connection of the resistor and capacitor. And that's very, very famous. Now, we call this output over input. The output over the input is a transfer function. And the general way of writing the general notation that's almost always used for a transfer function, and I say almost always because there's one blaring exception from the world of physics, but the transfer function used is capital H of omega. And one of the things that connections that I want to make today, sort of an extension that I will say very much an extension that I want to make today is this observation. Let's see, what color should I use? I think I'll use pink just to make sure. Okay, so I'm going to draw a connection here, and I'm going to go back to our very, very, very beginning of the course, where we talked about having a plot of a cosine, for example, or a plot in the time domain, and then being able to write it in the frequency domain, being able to plot it also as a function of frequency. So we have plots in the time domain, plots in the frequency domain, and here we have a function that's a function of frequency. So in a few minutes here, I'm going to show you how to plot that function in the frequency domain, but I should also be able to plot this in the time domain, and the notation for that function, which we haven't even considered before, is h of t. And so h of t, so if I figure out how to plot h of omega in terms of h of t, in terms of time, then instead of calling it capital H, I'm going to call it little h of t. Okay? Now, it turns out that we actually have looked at an h of t, and I'm going to show you where we looked at it. Let's see if I can find that. Let's see if I can, oh, darn it. Here we go. Here we go. It was this problem. I think this was a homework problem. And what we did was we talked about a delta function into a system producing a delta function response h of t. And so remember I used that h of t? Well, that's an example of an h of t. A delta function response is an h of t. If I express a delta function response in frequency, then I have capital H of omega. So here's the specific example, nothing to do with an RC constant. Well, maybe it does actually, because there's this kind of decay on it with a time constant. So maybe this is closer to this RC problem than we thought about. Sloppy as heck, but maybe it is. Who knows? And we looked at this kind of example where we had two delta functions and we had two delta function outputs. So this is the kind of connection that I'd like to draw today, or just mention briefly today. That there's a connection between this delta function response h of t and this transfer function capital H of omega. They're the same function. One is plotted in the time domain, one is plotted in the frequency domain. And so we've gone ahead here and very easily, just with some algebra and this use of a complex number, we were able to very, very quickly, just a couple of lines, derive the transfer function for H of omega. And from there, what we did was we noticed that we had the square root of -1 in there. We had j in there. And so we had to clear j from the denominator so that we could write our real part and our imaginary part. We wrote our transfer function, the magnitude of our transfer function, like that, and we wrote the phase response. Now, did we calculate the phase response? Maybe we haven't yet. Okay, that's the next thing to do then. That's where I left off. I knew there was something I'd forgotten to do. So the phase response, I'll go back to a serious color. The phase response is the inverse tangent of the imaginary part over the real part. And if I go back to this, notice that my imaginary part is omega RC over this denominator. And notice that my real part is this omega RC squared over the same denominator. And so if I take the ratio, the denominator cancels out. So I'm not even going to write down that denominator. If I write it down, all I'm going to do is set myself up for a a transcription mistake, and that's just gonna, it's gonna waste all the time. But I want you to remember that I am including that, I'm just immediately canceling it out. So the imaginary part over the real part for this particular example is the inverse tangent of omega RC over omega RC squared which is equal to inverse tangent of 1 over omega RC. And again, we know that the inverse tangent is a transcendental function. It has a Fourier series that has every single power, linear, quadratic, cubic, and so on. And if I'm adding all those together, I have to have a dimensionless number. Once again, I see the role of RC and omega as the dimensionless number, as omega being inversely proportional to RC, and RC having units of time, and frequency having units of 1 over time. So what I did was I plotted these two functions. I plotted the magnitude h of omega, and I plotted the phase of h of omega. And I didn't do a great job, but I did go to Excel, and hold on a second. Stop share and share screen again. And then there we go. You should be about to see this. So let's see. I defined an x as omega RC. So this is an example. Using this example, this is a dimensionless number. And whenever you can write something as a dimensionless quantity, you're one step ahead of the game. And so this omega RC coming out as such an obvious dimensionless number allows me not to worry about kilohertz. It allows me not to worry about mega ohms or microfarads. I'm just going to say, I'm going to write everything in terms of omega RC. And so when omega is equal to RC, when omega is exactly equal to RC, I'm going to have 1 I'm going to have 1. And so what I'm going to do for this is I'm going to plot 2 orders of magnitude below it and 2 orders of magnitude above it. Okay. So if this were a kilohertz, then I'm going to go down to 10 hertz, and I'm going to go up all the way to 100 kilohertz. So I'm including 4 orders of magnitude. 4 orders of magnitude in this plot. Okay, and that's very, very typical. That's very typical when we work with the frequency response of things like filters, like we're doing today. Is you're gonna think not in terms of 1 to 10, but you're gonna think in terms of 1 to 10,000. Okay, so we need a way of thinking about that. So here's 0.01 and here's 50. If I go 1 more, it's 100. And so I'm going 1 order of magnitude through these cells, another order of magnitude through these cells, another order of magnitude through these cells, and then a last order of magnitude through these cells. And what you notice here is I have to figure out a way. Oh, so then what I do is I plot over here. I have my, my function, which is the dimensionless number x divided by the square root of 1 plus x squared. So this is omega RC in the numerator and omega RC squared plus 1 to the square root power in the denominator. And so what I did was I calculated the function for 0.01, 0.03, 0.05, 0.1. Here's what it is at omega equal to RC, or that x equal to 1. It's an interesting number. It's square root of 2 over 2. Very interesting number to pop up like that. It's certainly worth noting and probably worth memorizing, or at least knowing that. And notice that for very low frequencies, the response is very small. For very high frequencies, we're getting pretty close to 1. 2 orders of magnitude above the RC cutoff, I have a unity pass. And so if I plot the frequency as a function of the transfer function, I get this kind of behavior. And this is a high pass filter, and this is a linear frequency scale. Okay. And really all it tells us is that it creeps up to 1, and we lose all information about these low frequencies. It's just a blur in there. And so what I did in this column here is I'm plotting the log of those frequencies. And I'm doing something that's kind of interesting. Notice that I'm doing 1, 3, 5, 1, 3, 5, 1, 3, 5. It turns out that if I do 1, 3, 5, 1, 3, 5, I get points in the log scale that are about equally spaced. And so here what I have are the log of those frequencies. And if I plot, instead of the linear frequency scale, if I plot the log frequency scale, I open up what's going on at the low frequency space. So here's a decade of frequency. Here's another decade of frequency. Here's another decade of frequency. And here's another decade of frequency. And so this is a much more common representation because we're dealing with orders of magnitude of frequency. It's much more common to take the log of those frequencies. Now, the other thing that is often done is to convert this linear vertical scale to something called decibels or dBs. And a dB is 20 times the log of the ratio of the voltages. It's 10 times the log of the ratio of the powers. And I'll let you chew on why that is. But it's 20 times the log of the ratio of voltages. And so now what I'm measuring, now what I'm plotting here is a high pass filter, dBs versus, or decibels versus the log of frequency. And this is called a Bode plot, B-O-D-E. So this is called the Bode plot, and this is the magnitude of the filter. And so you'll see that at 0 dB, I have unity gain, and then I roll off at about 20 dBs per decade. The difference between this is 1 decade, 1 order of magnitude, 1 decade, and I drop from minus 20 dB down to minus 40 dB in 1 decade. So this slope here is called a 20 dB per decade slope. 20 dB per decade slope. This is some of the terminology that electrical and computer engineers use when they're describing filter response. So mostly what I'm doing is giving you some conventions on plotting and telling you some vocabulary words. Now, this is the magnitude, and we can plot the phase as well. Please notice this roll-off from rejection of frequency components to pass of frequency components, low to high. It's a high-pass filter. Look at what's happening in the frequency response. I flip from, here's my plot of arctangent of 1 over x, 1 over omega RC. And I'm going from a pi over 2 response to a 0 response. And I'm flipping, I'm halfway in that phase transition. I'm halfway through that phase transition at omega equals RC. The log of 1 and the log of 1 is 0. So the crossing point, the 0 crossing point is I'm halfway through this phase reversal. So I'm going from a destructive interference where these frequency components cancel out and thus the signal is rejected, to a place where there's no phase response, and I add them constructively and they pass through. So the phase information, if you read it right, gives you exactly the same information as the magnitude response. You just have to analyze your filter in the phase domain, or thinking about the phase of the sinusoid signals versus just what the magnitudes are doing. And I think that's kind of cool. And somewhere way, way, way down the line, you'll learn that there's a formal relationship between magnitude and phase that holds for all physical devices. It's a pretty magic thing. It's pretty complicated actually to show, and so you'll probably get there somewhere in a couple of years. But it's really beautiful, beautiful result. But for now, you should notice that it's not a coincidence that this destructive interference to constructive interference is the same as rejection in the magnitude versus passing in the magnitude. Okay. So what I'd love for you to do is for your homework, I'd like you to go ahead and derive your transfer functions for your circuit, which is a current divider, not a voltage divider. And then I'd like you to plot plots like this. Use Excel and plot and do plots like this for your filter response. And I know the question is going to ask, gee, Duncan, will you send out this Excel spreadsheet? And I will absolutely send this out, but I will send it out on Wednesday. So you're going to have to struggle and work with each other to recreate as much of this as you can. And frankly speaking, if you plot something that looks like this on a linear scale, I'll be okay. But do try to think in terms of this log column, and do try to remember, if you can, remember that the dB is. And I think the book does a pretty good job of introducing a lot of this as well. So you can fall back to that. Okay? And if I have a feeling when I'm going to create the same filter, I'm going to create the same workbook, for Wednesday's class, and it's going to be a very simple replacement. And so I think if I sent this out, I just don't think you'd learn anything. So I'm going to let you be frustrated and hate me for a couple of days. And I know I'm actually being quite accurate about that. I know I've gone through this very quickly, but again, let me point out these columns to you one more time. Normalized frequency, X is equal to omega over RC. I'm sorry, X is equal to omega RC, WRC. And then I take the log of those frequencies, and I spend a little bit of thought about not taking too many points, because the log will smooth all that out. And then 20 log of the transfer function. Okay. All right, so I'm going to save that. I'm going to stop share on that. I'm going to go back to this guy here. And I'm going to switch gears a little bit. And I'm going to talk for the last 20 minutes or so about transistors and active devices. And this is 4/13/2020. Okay, so whenever I put a battery into a circuit, hold on. Share screen like that. There we go. Sorry about that. Okay, so whenever I put a battery into a circuit, I'm feeding the device some energy, and so I'm allowing the device to contribute power to the signal. So if I put an active device in my RC circuit that I just did, I can raise my pass from 0 dB to say 20 dB, or I can raise the output signal from 1 to 100. And that's really, really useful, because then I can distribute that 100 units of signal across more circuits. So I really can't scale in complexity, in size, I cannot scale unless I have gain, unless I have an active device, a controllable device. And the transistor is the first one that I'd like to talk about. And I'm going to talk about the transistor from a configuration point of view, because it'll make the video for Friday that much more accessible. So what I'm going to do is I'm going to start with a piece of silicon. And I'm going to do, the first thing I'm going to do, and this is talked very nicely about in the video, is I'm going to put some doping into a region like this. So the way I'm going to do that is I'm going to put that lacquer or photoresist across this entire area. I'm going to mask out this piece and this piece and etch away the lacquer or the photoresist. And then I'm going to bombard this with ions. And then I'm going to heat it to pull the ions into what's called a channel. Then what I'm going to do is I'm going to put some metal here, and I'm going to put some metal here. And then I'm also going to put some metal here and here. Actually, I'm going to cover the whole channel with metal, but I'm going to draw it just on its side like this. And these three metal pieces have names. That's the source, this is the drain, and this is the gate. And I want you just to pause and think for just a second about those words, because those words have meanings. Current starts with the source. It wants to get to the drain of this transistor. And the gate is going to decide whether or not those carriers, those electrons, are able to go from the source to the drain. Depending on what voltage I put on the gate, I can pull those carriers through, or I can choke off those carriers. So let me draw the same element again. I'm going to draw, there's my metal, there's my metal, there's my gates, my gate electrodes. And if I put one type of voltage onto the gate, the fields that go out from that voltage look like this and pinches off. The voltage applied to the gate can pinch off the channel, and pinching off the channel is a very descriptive phrase. It's not just gobbledygook vocabulary. It stops current flow. So depending on the voltage, I can either have current going through or I can stop current from going through. And in fact, if I vary G, I can have a whole set of conditions where I can let some current through, I can let a lot of current through, I can get more current through. So this, in the simplest way of thinking about this, transistor, this is my off state, and this is my on state. If current is flowing, then I have an on. If current is not flowing, my transistor is off. And because this voltage here provides fields to control this current, this type of transistor is called a field effect transistor or a FET. Now, in your book and in future courses that you take, you're going to get really confused because you're going to learn all kinds of different types of transistors. And what I've decided to do is just talk about one, which is the field effect transistor. I chose this transistor for two reasons. One reason is the effect from off to on is the simplest effect. It's much more simple than the other types of transistors that are out there. Very easy to understand a voltage throttling down this channel, pinching off this channel, than the weird effects in other types of transistors that were actually arguably developed or realized before this one. And the other reason that I wanted to talk about FETs and not the other types of transistors was that the FET, this field effect transistor, is far and away the dominant structure. Every single memory chip, every single microprocessor, or almost every single microprocessor that's out there uses field effect transistors in a process called CMOS. Okay, so when you read the article and when you watch the video, this is the device that they're mostly talking about making, is this field effect transistor. And when you talk about Moore's law, when you talk about a field of a microprocessor of all these numbers, all these transistors, and how small they are, this is far and away what's going on about 90% of those components. Okay, so I wanted to do this for a couple of reasons. One is because naturally in the flow of circuits, you move from passive components, which are resistors, capacitors, and inductors, to active components that require a voltage to operate. That V sub G has to come from somewhere. Where does it come from? It comes from a battery or a power supply that you plug into the wall. The computers that you're watching me on are plugged into the wall or have a battery, and those batteries are providing the voltage that all the gates in all the gazillion transistors that are in your device are requiring to turn these gates on and off, on and off, on and off, into an endless dance of processing those and processing those signals. Okay. So the progression from resistors to capacitors, resistors, capacitors, and inductors to active devices and transistors, I think, are a great place to start because they provide this switching. And they also provide the opportunity for gain. So two things, two regions of operations, switching and gain, can come out of these active devices which rely on an external power supply. Your cell phone has to charge. The battery in the cell phone is there to provide the power so that it varies pretty much 80%, 90%, so that it can regulate the flow of current through all these little channels. So this week, I'm introducing this type of device, and we will talk on Friday. You guys will watch this, and what I'm going to do on Friday, by the way, is I'm going to go around to each of you